solid ground beneath your feet right now. It feels unmoving and permanent. Yet, that sense of stability hides a restless interior where rock flows like slow honey over millions of years, and metal spins in a vast liquid ocean. Deep inside our planet, layers of different materials and temperatures interact in ways that slowly reshape the surface, building continents, opening ocean basins, and recycling crust back into the depths. The same heat that keeps the outer core molten also drives the slow motion of rigid plates across the surface, creating mountain ranges where land masses collide and deep trenches where ocean floor dives downward. Seismic waves from distant earthquakes travel through these layers and bounce or bend at their boundaries, giving us a detailed map of what lies below without ever drilling more than a tiny fraction of the way down. Satellite measurements of gravity and magnetic fields, together with the ages of rocks collected from the sea floor and the patterns of earthquakes and volcanoes, all confirm that Earth's interior is dynamic and that the continents and ocean we see today are temporary features in a continuous geological circle. Understanding this internal architecture and the process it powers allows us to see why the surface looks the way it does and how it continues to change. In the following account, we will explore those layers and the surface process they control, using clear language and the solid evidence that science has gathered, so the story of Earth's interior becomes as tangible as the ground they stand on. Every time a large earthquake occurs, the shaking sends out two main kinds of waves that race to the planet at different speeds. The faster waves push and pull the rock in the direction they travel and can move through both solid and liquid material. The slower waves shake the rock from side to side and can travel only through solids. By timing how these waves take to reach recording stations around the world, and by noticing where one type of wave disappears, scientists map the depth at which the material changes from solid to liquid or from one density to another. These natural signals, combined with the planet's overall mass, its slightly polar flattening, and the way it responds to the pull of the moon and sun, have built a reliable picture of the depth interior that matches laboratory tests of rock and metal under extreme pressure. Earth is built in concentric cells that differ in composition, density, temperature, and physical state. The outermost cell is the crust, a thin, rigid skin that is only 5 to 10 kilometers thick under the ocean, and 30 to 70 kilometers thick under the continents. Oceanic crust is denser and made mostly of dark, iron, and magnesium-rich rocks, similar to basalt. Continental crust is thicker, less dense, and richer in lighter elements such as silicon and aluminum, giving it a composition closer to granite. Because continental crust is buoyant, it rises higher and rarely sinks back into the mantle, which is why the oldest rock on Earth are found on the continents, while the ocean floor is everywhere younger than about 200 million years. The boundary between the crust and the mantle is marked by a sudden increase in speed of seismic waves, showing that the rock becomes denser and different in mineral makeup. Beneath the crust lies the mantle, a thick shell of silicate rock that extends nearly 3,000 kilometers downward and makes up the bulk of Earth's volume. Although the mantle is solid, the enormous heat and pressure allow it to flow very slowly over geological time, much the way a glacier of ice flows downhill. The uppermost part of the mantle together with the crust form the rigid lithosphere, which is broken into large plates. Below the lithosphere is a weaker zone called asthenosphere, where the rock is closer to its melting point and can deform more easily, allowing the plates to slide. In the asthenosphere, a small fraction of melt may be present, further reducing strength so that the rigid plates above can move with less resistance. Deeper still, the lower mantle becomes denser and more rigid under extreme pressure. Yet, it continues to participate in the low convective circulation and move heat outward from the core. Seismic waves speed up gradually with depth through most of the mantle because rising pressure packs the minerals more tightly, but they also show scattered regions of slow velocity that are interpreted as hotter, rising material and faster velocity regions that mark cooler, sinking slabs. At a depth of about 2,900 kilometers, the rock mantle gives way to the core, which is composed mainly of iron and nickel, with smaller amounts of lighter elements. The outer core is liquid seismic shear waves, which can travel only through solids, stop completely when they reach this boundary, while compressional waves slow down and bend sharply. This creates a wide shadow zone on the opposite side of the Earth, where almost no shear waves arrive and compressional waves are delayed or missing, providing clear evidence that a liquid layer exists. The liquid outer core is about 2,260 kilometers thick and is kept molten by residual heat from the planet's formation and by heat released as the inner core slowly glows. Within the outer core, swirling motion of the electrical conducting metal generate Earth's magnetic field through a self-sustaining dynamo process. The field is not static, it wanders, weakens, and occasionally reverses direction over thousands to millions of years, leaving a permanent record in rocks that cool from a molten state. At the center sits the inner core, a solid sphere roughly 1,220 kilometers in radius, despite temperature estimate near 6,000 degrees Celsius. The immense pressure keeps the iron alloy solid. Compressional waves speed up again when they enter the inner core, and weak shear waves have been detected traveling through it, confirming its solid state. Density increased steadily from the crust outward. Continental crust average about 2.7 grams per cubic centimeter. Oceanic crust about 3.0. The mantle from 3.3 near the top to 5.5 at its base. The outer core around 10 to 12, and the inner core 13 or higher. Density contrast measured by the way seismic waves accelerate or slow and by the planet's overall mass and moment of inertia. Match laboratory experiments on rocks and metal subjected to high pressure. The temperature also rises with depth, reaching roughly 1,000 to 1,500 degrees Celsius at the base of the crust, several thousand degrees in the deep mantle, and 5,000 to 6,000 degrees in the core. Although the exact values are refined by combining seismic data with mineral physics, the heat that powers the interior comes from two main sources: leftover energy from the collisions that assembled the planet more than 4.5 billion years ago, and the continuous decay of radioactive elements such as uranium, thorium, and potassium. This heat must escape, and the most efficient way is through convection in the mantle. Hotter, less dense material rise, while cooler, denser material sinks, creating a circulating pattern that exerts drag on the base of the lithospheric plate. The rising limbs of these convection cells are often linked to broader upwellings that can produce chains of volcanoes far from plate boundaries, while the sinking limbs are the cold slab of subducted ocean floor that can be imagined by seismic tomography as it descends hundreds or even thousands of kilometers. The plates themselves move at rates of a few centimeters per year, roughly speed at which fingernails grow, yet over tens of millions of years, though motion rearrange continents and open or close entire ocean basins. The rigid plates meet at boundaries of three main types, each producing distinctive geological feature and each leaving clear traces that can be measured today. Where plates move apart, magma from the mantle rises to fill the gap, cools, and forms new oceanic crust. This process, called seafloor spreading, occurs along a global network of mid-ocean ridges that wind through every major ocean and total more than 60,000 kilometers in length. Fresh lava erupts at the ridge axis, freezes into basalt, and is carried sideways as more magma rises behind it. The newest crust is hot and thin. As it moves away, it cools, thickens, and becomes denser. Heat flow measurements show the highest value right at the ridge axis and a steady decline with distance, matching the predicted cooling of lithosphere. Magnetic material in the cooling lava lock in the direction of Earth's magnetic field at the time of formation. Because the field has reverse polarity many times, the seafloor carries a symmetrical strip pattern of normal and reverse magnetism on either side of the ridge, providing a clear record of continuing spreading. The width of each stripe corresponds to the length of time the field stayed in one polarity. The weight of each stripe to the length of time the field stayed in one polarity, the pattern can be matched to the point to the independently date sequence of reverse reversal recorded in lava flows on land. Samples recovered by drilling show that the age of the ocean floors increased steadily with distance from the ridge, from zero at the axis to a maximum of about 200 million years near the edge of the basins. This conveyor belt process creates the ocean basin themselves. A new ocean begins when a continent is stretched and split by rising mantle material, forming a rift valley that eventually floods with sea water and widens into a full ocean as spreading continues. In the early stages, the rift may contain lakes and thick piles of sediment and volcanic rock. Once sea water enters, a narrow sea forms and then expands as the two sides continue to separate. Where plates converge, denser oceanic lithospheres sinks back into the mantle in a process called subduction. The descending plate blends downward, forming a deep ocean strand that can reach depths of more than 10 kilometers below sea level and slides beneath the overriding plate at angles that can be tracked by the location of earthquakes. With increase in depth along the sloping boundary down to 700 kilometers. As the cold slab sinks, it heats up and releases water and other volatiles into the overlying mantle wedge. Those floods lower the melting point of the mantle rock, generating magma that rises to form volcanic acts, chains of volcanoes that appear either as island chains when two oceanic plates meet or as continental mountain belts when an oceanic plate dives beneath a continent. The chemistry of the erupted lavas carry a distinctive signature of the recycled ocean floor material and the floods released from it. The subducted crust is eventually mixed back into the mantle, completing a recycling circle that keeps the total surface area of Earth roughly constant. When two continent plates collide, neither can subduct easily because both are buoyant. Instead, the crust crumbles, thickens, and is pushed upward, creating high mountain ranges and broad, elevated plateaus. The rock that once formed the seafloor between the continents are squeezed into complex folds and fault slides or are scraped off onto the edges of the land masses. Thickening of the crust can double or triple its normal thickness, and the deep roots of the mountains can be mapped by the way seismic waves slow down as they pass through the warmer, thicker crust. Over repeated circles of rifting, spreading, subduction, and collisions, continental crust grows by the addition of volcanic arcs, sediment splice, and fragments of older crust that are welded together. Transform boundary, where plates slide past each other horizontally, do not create or destroy crust, but connect the other type of boundary and produce frequent shallow earthquakes. The overall motion of the planet is therefore a closed system. New ocean floor is born at ridges, travels across the basins, and is consumed at strands, while continents, being lighter, remain at the surface and are shuffled into new arrangement. Evidence for this motion is abundant and mutually consistent. The distribution of the earthquake and volcano tightly follows the plate's boundaries, with deep earthquakes occurring only where coal slabs are sinking. Precise measurements of the distance between points on different plates made by repeated satellite observation show continuous movement at the rates predicted by the age of the sea floor. The fit of continental outline across the Atlantic, the matching of rock types, and the Asian climate indicators on now separate landmasses, and the progressive increase in seafloor ages away from ridges, all align with the same picture. Gravity measurements reveal the excess mass of the coal, dense slabs, and the deficits of mass beneath the ridges where hot material is rising. Magnetic surveys map the strip pattern across entire ocean basins, and the ages obtained from radioactive dating of record rock match the magnetic time scales. All of the independent data sets converge of the same rates and direction of plate motion. The continental crust itself records a longer and more complex history because it is not easily subducted. Fragments of crust dating back more than 4 billion years still exist in the stable interiors of continents. These ancient cores have been enlarged by successive collisions that added volcanic arcs and sedimentary wedges, and by the intrusion of large volumes of granite produced when thickened crust partially melt. The mountain belts formed in earlier collisions have been worn down by erosion. The roots from now exposed as broad shelves of ancient rock. At the same time, sediment eroded from the continents is carried to the margins and can be scraped off into accretionary weights or carried down with the subducting plate. The balance between the creation of new continental material at volcanic arcs and the occasional loss of crustal fragments keeps total volume of continental crust roughly steady over long periods, even while individual continents change shape and position. The presence of water is crucial in many of the processes. It weakens rocks, lower melting temperature, and allow the formation of silica-rich smelts that build continental crust. Without the continuous cycling of water into the mantle at the subduction zones and its return through volcanoes, the compositions and behavior of the crust could be very different. Heat load measurement at the surface show higher values over mid-ocean ridges where hot material is rising and lower value over cold ocean floor and stable continental interior. The magnetic field generated in the outer core cells the surface from solar wind and leaves it in imprint in cooling volcanic rocks, providing the magnetic stripes that record seafloor spreading. Changes in the intensity and direction of the field over time are preserved in sequence of lava flows on land and in the ocean crust, giving a continuous timeline that matches the ages obtained from radioactive dating of the same rocks. Seismic tomography, which uses the travel time of waves from thousands of earthquakes to construct three-dimensional images, reviews coal slabs descending into the lower mantle and broad hot regions, rising from near the core mantle boundary, confirming that whole mantle convection is active. Laboratory experiments that squeeze and heat mineral to the pressure and temperature of deep earth reproduce the seismic velocities observed, giving confidence that the interpaired composition and states of the layer are correct. The formation of a new ocean basin can be watched in its early stage in places where continents are actively rifting. The crust thins, valleys drop down along faults, and volcanic activity increase at Mantle material rise. Eventually, seawater invades the depression and a narrow sea forms. The continued spreading widens the sea into an ocean, with the mid-ocean ridge running down its center. Conversely, an ocean can close when the surrounding plates reverse direction and begin to converge. Subduction consumes the ocean floor until the continents on either side meet and collide, throwing up a mountain range and leaving only scattered remnants of the former seafloor caught in the collision zone. These circles of openings and closing have operated for at least the last 2 to 3 billion years, gradually assembling the continents we know and rearranging them into different configurations over geological time. Each circle leaves behind distinctive rocks assemblage, thick sequences of basalt and sediment from the ocean floor, high-pressure metamorphic rocks from the deep parts of subduction zones, and vast volumes of granite and fold sedimentary layers from continental collisions. Because the process operates so slowly, the landscape appears fixed on human timescale, yet the cumulative effect is profound. A plate moving at 5 centimeters per year travels 5,000 kilometers in 100 million years, enough to open or close a major ocean. The heat escaping from the interior is only about 1/10,000th of the energy Earth receives from the Sun, yet it is sufficient to drive the entire tectonic system because it is concentrated and acts continuously. The rigid plates act as the thermal boundary layers of the mantle convection system, and their motions are the surface expression of the deeper flow. In this way, the internal structure of the planet, its layers composition, its temperature gradients, and its ability to flow and generate magnetic fields. It's directly responsible for the distribution of continents and oceans. The location of mountains and volcanoes and the long-term evolution of Earth's surface. The same system also influenced the long-term carbon cycle by returning carbon-bearing sediments into the mantle at the subduction zones and releasing carbon dioxide through volcanoes, linking the deep interior to the surface environment over geological time. The evidence continued to accumulate. New seismic networks record more earthquakes and refined the images of slab and plants. Ocean drilling recovers addition cores that filled in the age and magnetic records of the sea floor. Satellite altimetry maps the subtle topography of the ocean floor that reflects the underlying plate boundary and the cooling of the lithosphere. Gravity and magnetic surveys flown by aircraft and satellites provide global coverage of crustal thickness and structure. Laboratory experiments subject rock to the pressure and temperature of the deep mantle and core, confirming that the material and phase changes inferred from seismic data are physically realistic. Computer models that solve the equation of heat transfer and fluid flow in the mantle reproduce the observed plate motions and the locations of major upwelling and downwelling when they are given the major heat flow and plate configuration of a layered Earth. As input. Together, these independent lines of observation demonstrate that the picture of the layered Earth with mobile surface plate is not speculation, but a well-tested description of how the planet works. The ground beneath our feet is the thin outer skin of a heat engine that has been running for billions of years, and the continents and the oceans are visible products of that engine's slow, relentless operation. Every mountain range, every ocean trench, and every volcanic island chain is a direct consequence of the internal layering and the convective motions that transfer heat from the deep interior to the surface. continually rebuilding the face of the planet on time scales far longer than human history, yet measurable with the tools of modern science.